Okay, so we're continuing our notes from yesterday. We're still in section 9.4. We never did take a quiz for this section. It went by so fast. I was like, oh, we should probably take a quiz. And forgot. So we're probably not going to have a quiz this section. We'll have the test. So this will be our last day of new stuff. We'll review Friday, review Monday, test Tuesday. So it's a pretty short section. But then chapter 10 will be a little bit longer. It's
Little short sections, at least there's less to remember for the test.
And then chapter 11 will be a short section again. So yesterday we learned about improper integrals, how to integrate if we have infinity in the bounds. But what do we do if we have to integrate with infinite discontinuities? So what do I mean by infinite discontinuity?
They're discontinuous forever.
Oh, I wrote it up there. A vertical asymptote. Okay. If we have a vertical asymptote, we can't integrate if our function's discontinuous, so we've got to do something about that. A vertical asymptote makes our function discontinuous. So if we look at this problem, how do I know where my vertical asymptote will be? Where the denominator is 0. So we have a graph. Let's actually graph this. I don't have my Inspire software up, so we're going to have to use calculators so that we can just get the general idea of why we do this next part.
So it's vertical asymptotes that give us trouble, not horizontal. Is that right?
Correct. Because if I have a horizontal asymptote, I still have area under the curve. If I have a vertical asymptote, I have that infinite amount. And you'll see when I draw the picture. So 1 over square root of x looks like this. Right? So, the horizontal asymptote is where we're doing like 1 to infinity. If I start here and go to infinity, and that's what we learned yesterday. What if I'm going from 0 to 1? 0, there is nothing defined there. There is no actual function at 0. The closer we get to 0, the higher the y value is, so we get infinitely high y values as we get closer and closer to the x value of 0. So we can't actually hit 0. I can't include 0 in my bound because I can't hit 0. So again, when we have these vertical asymptotes, we have to include the limit. The limit didn't care if we actually reached a y value. We just care that we got infinitely close. I can get infinitely close to 0, but I can't actually hit 0 itself. But what direction am I approaching 0 from? The positive direction. So I'm approaching, sorry, this is 0.
Yeah.
I'm approaching 0 from this way. So I'm approaching from the right. So when we did limits, limits assumed you were approaching from both directions unless you told it otherwise.
With the little plus.
Yep, with the little plus sign. So we're going to replace where our infinite discontinuity is with a variable, or with a or b again. Since our infinite discontinuity was on the bottom, we're going to replace it with a. So we have the limit as a approaches 0 from the right. We can't consider the limit as a whole, but we can work with it if we're approaching just from the right. Of the integral from a to 1, and I'm going to rewrite this at the same time so we can integrate it.
So 1 over the square root of x.
Well, also, that is 1 over square root of x. We can move the dx to the side. But we have to rewrite 1 over square root of x before we can integrate. How can I rewrite 1 over square root of x?
X to the negative 1/2.
Yeah.
X to the negative 1/2. Very good. So now I can just do my anti-power rule. We add 1, divide by whatever we get after we add. Here from the right. Anti-power rule would give us x to the positive 1/2. What if I divide by positive 1/2? What do we get for the coefficient?
Maybe 2.
2. Positive 2, because we do the division after we add. Where we're doing so many derivatives and integrals together, it's very important we pay attention to those details, because they're so similar, it's easy to mess it up. So we have the limit from a to 1. We can now do the fundamental theorem of calculus. So it's almost exactly the same as when we had infinity in the bounds, except we just have to decide, are we approaching from the right, are we approaching from the left? Where is our infinite discontinuity?
So why do you have 2 in front instead of 1/2?
Because you were.
divide by
Yeah.
1/2.
And if you divide by 1/2,
Oh.
that's the same as timesing by 2/1.
Okay.
So this fraction wise, that's why we have the 2 out front. So we do fundamental theorem of calculus, 2 times 1 to the 1/2 minus 2 times a to the 1/2. So limit-wise, this first part, still a constant. I just realized, oh wait, no, I am recording. Hooray! Okay. So limit of a constant is a constant still. Now, what's going to happen if I plug in 0 here?
It's gonna be 0.
It's going to be, well, it's 2 times 0 to the 1/2, so it's going to be 0. Now, so we're wondering, why did we have to change this in the first place? What if we were back here and we tried to plug in 0? That gives us a problem because it was 1/0. So even though we're approaching from the right, we don't have to worry about that in this particular case, because now that I have a to the positive 1/2, I can plug in 0 just fine. 0 doesn't give me trouble anymore. So again, I know it seems unnecessary. We talked about that yesterday. It almost seems unnecessary to replace it with the limit, but it's one of those picky math things that you have to do to get points on the AP test. So we got to do it anyway. So we know the limit of this is 2. We know this, we can actually plug in 0 because it doesn't give us trouble anymore. So the final limit is 2. So that means the integral from 0 to 1 is 2. We have an area under the curve of 2, or a displacement of 2. If this was, this was a temperature cooling, which it wouldn't look like this, but just pretend. If it was a temperature cooling problem, we would have cooled 2 degrees. So then the last one is, what if we have our discontinuity in the middle of our integral? Where is our discontinuity on this one?
X equals 1.
At x equals 1. 1 makes the denominator 0. So we have to split this into 2 separate integrals. We're okay with the bounds. We're okay with 0. We're okay with 3. What we're not okay with is 1. We can't integrate if our function is discontinuous. So we have to split this into 2. We have to say the integral from 0 to 1 of 1 over x minus 1 to the 2/3 dx plus our second integral from 1 to 3 of 1 over x minus 1 to the 2/3 dx. And then we're going to have to replace both of these with a limit. We just have to decide which side are we approaching from. Well, if I'm going from 0 to 1, let me see if I can do this backwards. Here's 0, here's 1. What direction do I have to approach 1 from if I'm starting at 0 and heading towards 1? From the left side. So this first integral would be from, let's see, b approaching 1 from the left. 0 to b. And I'm going to rewrite this to make it a little easier for us to integrate. So to the negative 2/3 plus, And then we have to do the integral from, oh, wait, limit first. It's the whole purpose. Limit as a approaches 1. And if I start at 1, no, if I'm going from 1 to 3, so I have to approach, I can only use the values between 1 and 3. I have to approach 1 from the right, because I can only use values between 1 and 3. So we are approaching from the right this time.
I'm not gonna lie, I'm a little confused right there. She's
Yeah.
like,
It's easier if I draw a picture. 0, 1, 3. Our first integral, I can only use those values because we're going from 0 to 1. So I have to travel from over here somewhere towards 1. So I'm approaching from the left side. I'm approaching from the left side of 1. But on the second integral from 1 to 3, I can only use these values. So I have to approach 1 from something over there. Doesn't really matter where. I can start it at 3, I can start anywhere. Just for
So
saying,
you always have to approach the 1.
well, you have to always approach the discontinuity.
Okay. Okay. That makes more sense.
And yeah, it's easier when we see the whole picture, not just try to imagine the picture in our head.
well, I just saw hand numbers.
So now we can integrate. What method do we have to use to integrate this? And they're going to be the same integral because they're the same function. U sub. But what is du going to be? What's the derivative of x minus 1? 1. So u sub's not really going to make a huge difference in this. It's not going to make an impact. So I can basically do anti-power rule like I would normally, just I'm going to have x minus 1 on the inside. So it's 2x minus 1. The whole point of u sub is we get that extra 1/2. But if it's just 1, if we get an extra 1 that we're multiplying by, that doesn't do anything. So we can kind of skip u sub, but only if the derivative of the inside is 1.
Okay.
So we have limit as b approaches 1 from the left. We add 1 to the 1/3. We divide by 1/3. Is same as multiplying by 3. Evaluated from 0 to b plus limit as a approaches 1 from the right. We do it again. It's going to be the same integral. 3x minus 1 to the 1/3 from a to 3. Now we start plugging in. We do our fundamental theorem of calculus. Limit as b approaches 1 from the left. 3 times b minus 1, 1/3, minus 3 times 0 minus 1 to the 1/3, plus, limit as a approaches 1 from the right, 3 times 3 minus 1 to the 1/3, minus 3 times a minus 1 to the 1/3. We just did our fundamental theorem of calculus twice. And now again, if we have, even though we're approaching from the left, if it doesn't cause us any trouble to plug in 1, we just plug in 1. What would we do if it does cause us trouble to plug in 1? If I can't just plug it in, what are some other ways we can take limits? We can do graphically, so we can plug in values pretty close to 1 and see a pattern forming. We can't just plug in we can't just plug in one value, we have to see a pattern forming, so we'd have to plug in from the left, we'd have to plug in 0.9, 0.99, 0.999, 0.999 and see what's going on. Or look at the picture. Maybe we'd have to apply L'Hopital's rule. So there might be some ways we have to do our limits, but what happens if I plug in 1 here?
0. 0.
0, can we do 0 to the positive 1/3?
It's
But 0 to the negative 1/3, that would cause us a problem. But 0 to the positive 1/3 is just 0.
So it's just the 3 times the 3 minus 1.
Yep. So the negative 3 times the 0 minus 1. 0 minus 1 is negative 1. And what's negative 1 to the 1/3?
Oh.
What do we mean by the 1/3?
Oh.
Cube root of negative 1. What is the cube root of negative 1? That is the square root of negative 1, or the fourth root of negative 1.
Oh, it's negative 1.
It's negative 1. Cube root means what number multiplied by itself 3 times. I can multiply negative 1 by itself 3 times and still get negative 1.
So cube root, you can use negative numbers.
Yes, cube roots, you may use negative numbers. Well, odd roots. Any odd root, you can use negative numbers. Any even root, you cannot. And then we go to this one. 3 minus 1 is 2. So we have plus 3 times 2 to the 1/3. Minus what's going to happen again when we plug in 1? 0. So that goes away. So we have 3 plus 3 times 2 to the 1/3. I'd probably leave it like that, or I'd get a decimal. Because 2 to the 1/3 we can't do nicely. 2 to the 1/3 is a decimal of some sort. So we'd either leave it exactly like that or find the decimal. So that finishes up what we were going to finish talking about yesterday. And then now we're going to talk about something called the comparison test. We're going to use our knowledge of improper integrals to still be able to say some stuff about integrals we can't actually integrate. We do still have some integrals we can't integrate. We can pretty much derive anything we want to. But there are some integrals we do not have rules that we can use to integrate them by hand. Your calculators can still approximate the area, it can calculate it to a fine enough that we get it. But some integrals we just can't do by hand, even though the calculators could still do it. Sorry. So we're not going to be able today to say what it converges to. All we're going to be able to do is decide if this function converges or not, or this integral converges or not. So our final answers won't be like 5. It'll be converges or diverges.
So we're going to go through lots of messy words to find a simple answer.
Yes. Okay, so if we have 0 is less than or equal to f is less than or equal to g. So let's say this is my function g of x. We know f of x is smaller than this function. We don't know what's going on with f of x. It can have whatever it wants, but it's just smaller than g of x, for sure. Although mine isn't exactly a function anymore. My squiggle should not have gone sideways. So that was still considered a function.
Are they both functions, or are they
They're both functions.
just one is
Yep.
really weird?
Yeah, they're both functions, just one is smaller than the other. So f might be nice. Maybe f looks almost exactly like g, but it's underneath it. But it doesn't have to. It's just any function smaller than g.
So that squiggly line is the
Yes.
basically what I'm asking.
The squiggly line is the function f of x.
Okay.
I did, yeah, I made them sideways a little bit, so then I erased it and tried to fix it. 'Cause
So what's the red line?
it's another possible function f.
So there's two f of x's.
No, the other one's g of x. Oh.
The black one's g of x.
Yeah.
The
There's
straight
two red ones.
f of x,
Do you
and then
want to
there's
draw
squiggly
both
f.
She was
of
just
ones, or-
proving.
No, you don't have to. I was just saying the f of x could look nice.
It
It
could
doesn't
be
have to.
anything.
Yeah, it could be anything as long as it's under g.
I was wondering how f of
Okay.
x was two functions.
So if g of x converges, when we say converges, we say it's going to get closer and closer to the x-axis. So when we're adding area, then we're adding zeros basically over and over again. So if g of x converges, and we know these are bigger than 0, we know it's not going to go under the x-axis, what is that going to force f of x to do? If this g of x is getting closer and closer to the x-axis, and we know f of x is always smaller than it, or possibly the same height, what's going to happen to f of x if g of x is going?
Done.
It's converging. If you have a big function over a smaller function, and you have a bottom limit, it's got to converge because there's no place for it to go. It can't go down underneath the x-axis. It can't go above g of x, and if g of x is going to meet the x-axis, it converges.
Intersection.
So if the integral of g of x dx converges, then the integral of f of x dx converges. Again, assuming f is smaller than g. It's all based on that assumption. If we don't make out that assumption, then this doesn't work.
Okay.
So what if we had the other direction? I'm going to draw a smaller graph up here. I should have left more space, but we don't have more space. What if, again, assuming f of x is smaller than g, but this time f of x is diverging. It's going like this. And we know g of x has to remain bigger than f of x. What's going to happen with g of x? It's also going to diverge. We can't go below f of x. So g of x also diverges.
What's the assumption you have to make? That it will-
Still that f is smaller than g. It's still based on that assumption that f is smaller than g.
So basically, if one does something, then the other does the same.
But what if I said f of x converges? What do we know about g of x?
It could diverge.
It could diverge. If f of x is converging, g of x could go back up like this. It's still
Yeah.
bigger than f. So that's why we have to specifically say we can't say if g of x diverges, f of x diverges. We have to be very specific, and only these two conclusions can happen.
Okay.
So let's take this function. The integral from 1 to infinity of e to the negative x squared dx.
Any games?
Yeah.
Convergence or divergence?
So we have to decide, will this converge or will this diverge?
Ladies and gentlemen, welcome to
And
Convergence.
if we could integrate this by hand, we'd just go do our integration. But e to the negative x squared, how would I integrate something like that?
Very carefully.
We would have to try u sub, but when we try u sub, so don't write this down because it's not going to work. When we try u sub, we get dx over negative 2. If we go to replace, we get e to the u times du over, oh, I put that in the wrong order. This should be dx, this should be du. Du over negative 2x. I can't integrate if I have an x and a u in the same function, and x won't cancel with anything. So u sub fails. So I cannot integrate this by hand. Now, the hard part is we've got to pick a function. we should decide first if we think this is going to converge or if this is going to diverge. So we've got to kind of consider, what do we think is going to happen when we plug in infinity? If we have e to the negative infinity squared, what do we think is going to happen?
Yeah. It'll.
Wait, can you say that one more time?
Infinity.
E to the negative infinity, and the squared is only applying to the infinity, not to the negative. Yeah. And what's anything to the negative infinity? When you have negative infinity as your exponent.
0.
0.
Oh.
Okay, remember we could rewrite it. We could write it as 1 over e to the infinity.
Yeah.
Okay. So we do think this will converge because that hit 0. So we think this is probably going to converge. So I want to prove that this function converges. So I need a function bigger. I'm going to say that function is f of x, and I want to pick a bigger function so that I can prove it converges. If I wanted to prove it diverges, then we would say the function we're working with is g of x, and we want to pick something smaller. So we're going to say f of x is e to the negative x squared. And we want to pick g of x so that it's bigger. So that's the hard part on this one. If we get to pick a random function, what random function do we pick?
This is where they make it.
2e to the negative x squared.
Okay, would we still be able to integrate that though if we have negative x squared? No, that's a problem. We are limited to functions we can integrate or else we can't decide if it converges or not. So, we need to decide something that is bigger than negative e to the x squared that we can integrate. So I am going to rewrite this as 1 over e to the x squared to help us think about this.
What about e to the x squared?
Okay, could we still integrate e to the x squared though?
No.
E to the x squared is definitely bigger.
Yeah.
Okay. E to the x. Did that work? That's not the one I was thinking of. So e to the x is definitely bigger, but it diverges.
yeah.
It doesn't converge. We need something that converges. Okay? Let's consider that. So e to the negative x, let's think of it in our fraction form again. Is this bigger than this? Why? Because you're dividing by a smaller number. This one's dividing by a bigger number than this, so these are actually smaller numbers when you perform that division. So e to the negative x is the one we're going to pick. So we want to integrate now from 1 to infinity e to the negative x to see if that converges, and if that does converge, then so will e to the negative x squared. So this is something we did completely yesterday, integrating 1 to infinity. So I'm going to give you guys a chance to integrate this yourself. I'm going to give you 5 minutes. Might need some help since she wasn't here for the lecture, but it's okay. Okay, so I'm going to have you guys try and integrate that yourself first before we talk about it together. So what did we get when we went through and integrated this? 1 over e. So that means the integral did converge to something. We don't have to just converge to 0. We have to converge to any actual number. Any number. So now we need to make our actual conclusion, though, because we were trying to originally talk about this integral. So AP test-wise, I can't just state that, yeah, that integral is going to converge because the other one did. We have to state why. We have to state because e to the negative x squared was smaller than e to the negative x, then the integral of 1 to infinity of e, so let's write it up. since e to the negative x squared is less than or equal to e to the negative x, and the integral from 1 to infinity of e to the negative x dx converged, then the integral from 1 to infinity of e to the negative x squared dx converges. I know it's a pain, but you do need to be that specific. If you just said, hey, it converges, that's not enough. The reason it converges is because that function was smaller than the other function, and the other function's integral converged. So then I just want to try one where we practice what we're going to choose if we're diverging. And if we're looking and we think, hey, this is probably going to diverge, how we choose our function. Does everyone have this down before I move to the next page? So we have the integral from pi to infinity of 2 plus cosine x over x dx. Now we think this is probably going to diverge. Why do we think trig functions are going to diverge? It just keeps going up and down. It's never going to converge to a certain point. It doesn't necessarily go to infinity either, but it's not going to converge, so it's probably going to diverge. So we think it's probably going to diverge, which means I need to pick a function smaller than it. So what do we know about cosine?
It goes like
Goes-
this.
And it goes between -1 and +1 only, right? So at most, what's the biggest it will ever be? 1. The biggest it will ever be would be +1. The smallest it would ever be is -1. So we definitely want this to be smaller. We kind of check and see what would happen. If we had a +1 there, we'd get 3 over x. If we had a -1 there, we'd get 1 over x. So we want to pick the smallest one because we want to make sure it's definitely smaller than 2 plus cosine x. So we're going to pick 1 over x as our function that is smaller. So then again, we integrate. This one we don't have to do u sub, so when we integrate it's going to be easier. And hopefully now when we see these infinities, the limit part's not as difficult anymore either. We replace limit as x approaches not x, b. We hope the limit part is easier. Apparently it's not. Pi to b, 1 over x dx. What's our integral of 1 over x? Something we should have memorized. Natural log, absolute value x. It doesn't always make a difference to have the absolute value there, but again, it's something, if you did not include on a free response question, that, yeah. If it was multiple choice, most of the time you could just drop it and not worry about it. Free response, gotta be careful.
I can see a corrector just sitting there correcting paper, and all of a sudden they start yelling at me. Oh, you fool, why didn't you do this?
Curses.
Curse.
Sorry, mine got squished. That's minus natural log of pi and absolute value.
No, it's soft.
Okay, so now we consider what's going to happen when we plug in infinity. Natural log.
It's gonna be
What's natural log as we go to infinity? Infinity. And infinity minus a number is still infinity.
Infinity laughs when it has numbers minus from it.
Exactly.
So
Okay.
it diverges.
So it diverges. So again, sorry, my brain froze for a second. We need to make our
Spring thaw.
conclusion. This problem is not finished. Since,
The lin of what? Is that pi?
yes, sorry, ln of pi, it got squished. Since, and that's not really correct grammatical English, but guess what? They don't care if your grammar is correct. That's okay. Only if your math is correct. So since,
1 over x is smaller than.
yes, 1 over x is smaller than
What is she?
equal to 2 plus cosine x over x. And integral from pi to infinity of 1 over x dx diverges. Then the integral from pi to infinity of 2 plus cosine x over x dx diverges. Yes, we are writing novels today.
It prepares my pen.
So the hardest part again is going to be choosing our functions.
It's like marriage takes forever.
Usually we try to kind of pare them down and get rid of any extra stuff. So for example, I'm not going to do that anymore. I'm just going to go to the blank page. So everyone have this down? Okay. Ignore the type words at the bottom. I'm changing.
Functions that probably converge. Oh, wait. My goodness. I didn't even.
What if I had 1 over x squared plus 1? First, again, we have to decide, do we think this will converge or diverge? So we kind of see what's going to happen if we plug in infinity.
It goes to 0.
Goes to 0. So probably it's going to converge.
You want me to write this down?
No, this one's just more of thinking about it. If you want to, you can.
Just
It's going to converge, so we need to pick a function bigger or smaller. Bigger.
Because that then needs to converge, and that would show that it will converge.
So what can I do about this? How can I simplify this so we get a bigger function? What about this could I kind of get rid of because it won't have a huge impact?
Plus 1?
Plus 1. Is this bigger
Barely.
than the other one? But is it bigger?
Yes.
Yes. I don't care if it's barely bigger. It could even be equal to. It's bigger.
Especially if you plug in.
So a lot of the times we're kind of trying to pare these functions down so they're simpler. What if I had something like this? Again, what could I get rid of? And this looks like if we plug in infinity, 1 over infinity is going to converge. So what could we get rid of? But we can't square it out of nowhere. We can't square the whole thing. We're trying to make it simpler. We're trying to get rid of stuff, not by using opposites, by just dropping it off to make this function simpler. So what did we get rid of in that one?
The one.
The plus 1. A lot of the time if we're plussing something like that, plussing a number, we're going to try and get rid of it. And what happens if we get rid of the plus 1? What's the square root of x to the 4th?
X squared.
X squared.
But isn't x, or the square root of 1 just 1?
Yes.
So couldn't it just be x squared plus 1?
Except
But that would still be.
plus sign. We cannot square individually when there's a plus sign. We can square individually if there's divide or multiply.
Okay, so you can't do the square root of x to the 4th plus 1. You can't do the square root of x to the 4th and the square root of x.
Yes.
Because combined, it's just a function, and so you'd have to have what times what equals that function. Whereas if they were separate, you could just square it.
Yep.
Okay. That makes sense.
Okay, so your homework.
Oh, homework is my favorite part.
Yes. So
I
excited.
get to write down the assignment, I get all excited about it, yeah, I can do it, and then I go and I do it, and things change.
I tried checking a little more carefully, so I think
That there's, what,
that,
there's no tricky,
yeah, there's no tricky things that we talked about, all this tricky.
like, taking it out of context so you can put it back in context.
Yes.
Oh, I love those. Then I get to go talk to my
Hopefully.
favorite teacher in the world.
Yes.
No sarcasm